Hello everyone, I'm Haoyang from Central South University. I share our research, cutting the request completion time in key-value stores with distributed adaptive scheduler with you. Today, key-value stores have been already the basic building block of large-scale cloud applications. One of the key performances is the request completion time, which is mainly decided by the time of waiting for servers. Thus, the scheduling of serving sequence is important. Scheduling in key-value stores faces following challenges. It should be highly adaptive and distributed. In this paper, we formalized and analyzed the scheduling problem, then identified the challenges. Based on this, we designed DAS which takes the server's load and performance into consideration. It reduced the mean completion time of end requests in heterogeneous and dynamic conditions. Finally, we evaluated DAS from the simplest offline conditions to the real large-scale conditions. DAS achieves lower mean and tail completion time than others. The present situation of key-value stores gives birth to DAS. Servers' inner mechanism makes their performance heterogeneous and time-varying, and the traffic characteristics make servers load unbalanced and dynamic. In addition, light-weighted key-value access operations limit the centralized scheduling. However, typical scheduling schemes can't adapt these characteristics all, such as the default FCFS, SRPT, and Wing SBF. Some other work are inspired but not suitable for this case. For example, C3 awares server's performance by piggyback information. ARPT last takes server's load into consideration, and the centralized scheduling for core flows is also inspired. Before introducing the designing, we formalized and analyzed the scheduling problem in key-value stores firstly. For each request, it contains lots of key-value access operations. We split the keys have the same target server into a key set. Obviously, the completion time of a request is decided by the latest completed key set, and the aim of scheduling is providing a serving order to minimize average completion time. Then we analyzed this problem started with offline condition, where all of the requests arrive in the beginning. In the simple condition with one server, SJF is optimal. When there was only one client, the problem degrades to concurrent OpenShop problem, which is NP hard. So the scheduling problem in key-value stores is NP hard too. ARPT last provided a too approximate solution in this condition. When there were multiple clients and servers, the system becomes more complex. The online condition is much harder to analyze. When there was only one server, SRPT outperforms than default FCFS and primitive SJF. When there was only one client, the awareness of dynamic server information should be also considered. When there were multiple clients and servers, the highly skewed traffic would bring new challenges of unbalanced capacity allocation. We show two examples to illustrate the scheduling process. First, SRPT. The key set size is shown in the chart. SRPT will calculate the request's remaining processing time and assign priority inversely to it. Servers schedule key sets according to this priority. Then we show the combination of LRPT last and FCFS. The client firstly calculated the load of each request and send them with load ascending order, and the servers serve cases according to their arrival time. Based on the above analysis, we can know the designing should be distributed, adaptive, and heuristically. And our solution is DAS. We decoupled this problem from client view and server view. Based on this, we designed the framework of DAS. First, clients measure the load of each server and decide the order of sending requests by ARPT last. Second, clients aware the server's performance via piggyback information, then assign the SRPT priority for each request before sending. Last, servers schedule the cases according to the SRPT priority. To avoid SRPT disturbing the sending sequence of LRPT last, DAS client send cases via one-by-one pattern. With this framework, DAS performs well in above example. The details of LRPT last short is shown as following. To avoid the load, we use the consume time of cases to calculate server's capacity, then measure the load according to it. The SRPT part is split into two. On the one hand, clients obtain service rate via the feedback information and assign priority according to it. On the other hand, servers schedule the cases according to the priority. To explore the performance of DAS, we conduct extensive evaluation. We built testbed via SymPy and compared DAS with FCFS, SRPT, and Ming SVF. Under the offline condition, when server performance is homogeneous, DAS achieves the best performance except in mailing to one condition, because DAS degrades to SRPT in this condition, and the one-by-one sending brings slightly extra overhead. When the server performance is heterogeneous, DAS is also the best. The online homogeneous condition is similar to the offline one. We also test the impact of system utilization. DAS outperforms than others no matter the utilization is heavy or light. Furthermore, we simulate the scenario of server performance changing with time in key value stores. DAS achieves the lowest average completion time. After the introduction of heterogeneous server performance, the advantages of DAS are further expanded. Finally, we built a large-scale simulation close to the real scene. DAS reduced the average completion time by nearly half compared with the default FCFS, without losing tail latency performance, and outperforms than SBF2. To sum up, this paper analyzes the scheduling problem in key-value stores and designs DAS algorithm based on this. The test results show that DAS can effectively reduce the average completion time and achieve the similar tail latency to FCFS and much better than SBF. That's all. Thank you for listening and welcome the questions.